Okay, so the purpose of this short video is to kind of introduce the following, the Calculus 3 course that we're going to be working through. So, Calculus 3 is essentially what we're going to be doing is we're going to be taking the fundamental ideas from single variable calculus, those being your standard limits, the classic derivative, and the integral. And we're going to be generalizing them into R3 and, R4, R5. R3 represents 3D space. And R3 is actually called a Cartesian product. There's actually, we're going to talk a lot more about that in a couple videos. But the 3 represents the dimension of the space. So 3D space, R4 is 4D space, R5 is 5D space, and Rn is an nth dimensional space. So we're going to be working to get limits, derivatives, and integrals into 3D space and ND space. So, when we think of a limit, we think of it as whatever, like, what value are we approaching at this point, as we approach this point? And if that point doesn't exist, are we approaching some finite value? Or is there some sort of issue that makes us unable to find the limit? Whereas in Calc 3, the issue with limits is that, well, let's look at it geometrically. If we have like a 3-dimensional shape, like a this is good. Say we have a 3D space, not unlike this one. And we want to find the limit. We want to find the limit as x approaches some point over here. So yes, we come in from the x direction, we come in from the y direction, or we come in from the negative x direction, we come in from the positive and negative y, but now we also have this direction, we have this direction, we have this direction, we have this direction, we have this direction. In other words, we have an infinite number of directions that we have to come in from and check if that limit exists. Just because the limit going from the negative x direction and from the positive x direction exists, which was our only contingency for single variable limits, doesn't mean that a multivariable limit exists. And therein lies one of the biggest cruxes of Calculus 3. As far as derivatives go, we're going to be, of course, finding lines tangent to 3D curves, but we're also going to be finding planes tangent to 3D curves. And we're going to be making approximations of those surfaces using those tangent planes, as they're called. And of course, integrals, we're going to be finding the area underneath those shapes. So it could be like a cylinder. It could be a cylinder with a funky roof. It could be just a singular path along a surface. It could be many, many different things. And of course, we're going to be working with vector fields. Vector fields is a fundamental idea in physics, in electrical theory, in any engineering course. You're always going to see vector fields because a lot of things behave like fields. So we're going to get started in the next video with vectors. We're going to talk about the dot and the cross products. And we're going to talk about these quadric surfaces, these 3D parabolic surfaces, or 3D surfaces, really. And then we're going to go on to the differentiation, the partial derivatives, these gradient vectors, and Lagrange multipliers. So partial derivatives is, of course, differentiating in 3D. And Lagrange multipliers are essentially optimization from single variable calculus brought into 3D calculus. And then in terms of integration, we're going to talk about multiple integrals. So that is finding the integral of a function over x, y, and z. And then right at the end, we're going to use everything that we learned from here and from here. And we're going to come full circle and go all the way back and introduce the 3 fundamental theorems of vector calculus. And those 3 fundamental theorems, I state them over here. I'm not going to talk about them. They're very important, and we're going to see them later on. But I just have them stated here so that you can understand that this is what we are working towards. And as far as that is our goal for the course. Thank you so much for watching, and please subscribe if you enjoyed.